So imagine bringing home this massive, hyper advanced, incredibly expensive new appliance.
Oh boy.
Right. You wrestle it through the front door, you finally find an outlet, you hit the power button, and instantly half the house just goes completely dark.
Yeah, you blew a fuse.
Exactly. You didn't
Yep.
buy a broken machine. You just plugged this futuristic piece of tech into a house that has, faulty, aging wiring.
Right.
The appliance doesn't fix the wiring, it just draws so much power that it exposes every single hidden short circuit in the walls. And while we're seeing this happen across the tech industry right now with artificial intelligence.
We really are. I mean, it is the defining engineering challenge of the moment. You've got all these teams rushing to deploy large language models and autonomous agents,
Yeah.
but they were dropping them onto these brittle, classical distributed systems.
Hmm.
And that is exactly why we are jumping into this deep dive today.
Welcome, everyone. I'm your host, and I'm thrilled to be here with our resident expert to unpack a really fascinating source. We are looking at Premjit Vidyadharan's revised July 2026 manual on system design for the AI era.
I'm so glad we're covering this. The mission here isn't just to, talk about the magic of AI. It's to bridge the gap between those hard-won lessons of traditional system architecture and this completely chaotic, probabilistic new world we're entering.
Right, because the foundational rule for you, the listener, is that you cannot abandon decades of proven engineering principles just because the letters A and I happen to be in your architecture diagram.
Totally. I mean, before we even whisper the words autonomous agent, we really have to establish the hard physics of how any system handles traffic and failure.
Because AI multiplies those challenges, right? It doesn't
Okay.
bypass them at
Oh,
all.
exactly. It does not bypass them. Any system design has to start with four basic numbers.
Okay, lay them out.
You've got expected scale, acceptable latency, acceptable staleness, and acceptable downtime. Every single decision, every box you draw on the whiteboard, it has to be justified against those specific numbers.
Because saying you want the system to be fast isn't a requirement.
Right. Fast is just a wish. Saying you need responses under 300 milliseconds at the 99th percentile during a flash sale, well, that is a real engineering requirement.
Right, and to hit those numbers, we are assuming you are already scaling horizontally, using stateless application servers so load balancers can route traffic anywhere.
Yeah, horizontal scaling is table stakes, but there is this massive trap when sizing that fleet. The math catches so many teams off guard.
Okay, let's unpack this. Walk us through the trap.
So say you're building a system that needs to handle 6,000 requests per second at peak.
Okay, 6,000 RPs, got it.
And your load testing shows that a single node can confidently process, let's say, 250 requests per second.
Right, so the naive math there is pretty simple. 6,000 divided by 250 equals 24.
Yep. So you spin up 24 nodes, maybe you spread them across 3 availability zones, and you call it a day.
Which guarantees a massive outage the second your cloud infrastructure has a hiccup.
Exactly. Because that naive math completely ignores failure states.
Yeah.
I mean, if your budget dictates that your architecture must survive losing an entire availability zone.
Meaning 1 out of your 3 zones just goes completely dark.
Right, exactly. Then those surviving 2 zones have to instantly absorb that full 6,000 requests per second.
So if you only have 2 zones left, each zone suddenly has to process 3,000 requests per second.
You got it. And at 250 requests per node, how many nodes do you need in each zone?
You'd need 12 nodes in each of those 2 zones.
Right. But remember, you have 3 zones total in your normal setup.
Ah, so you actually need 12 nodes in all 3 zones, which brings your total to 36 nodes, not 24.
Exactly. You have to over-provision by 50% just to survive that one specific failure scenario. That is what we call N-1 capacity planning.
Wow. Because without that math, just a single severed fiber optic cable takes down your entire platform.
It does. And how the system handles a struggling component is honestly just as critical.
Yeah.
Like a very common anti-pattern here is the retry storm.
Oh man, I see this constantly. You have a calling service hitting a database or maybe a third-party API, and the dependency slows down.
Right. It doesn't fail completely. It just gets sluggish.
Yeah, it gets sluggish. So the calling service hits like a 500 millisecond timeout, and it automatically retries the request. To me, it's like a stadium where one exit door gets jammed.
Oh, that's a great way to think about it.
Instead of waiting patiently, the entire crowd just starts banging on that exact same jammed door at the exact same time. Why does adding a basic retry make the outage so much worse?
Because it creates a total death spiral. I mean, when a dependency slows down, the calling service is holding a thread open, just waiting for a response.
Yeah.
When it times out and retries, it opens a brand new thread. So now that struggling dependency has double the incoming load.
Oh, wow. So it gets even slower.
Yep. More callers time out, more threads get opened, and literally within minutes, that slow dependency has consumed the connection limits and thread pools of every single service that talks to it.
So from the engineer's dashboard, the underlying database might technically still be functioning, but the whole platform just looks dead.
Exactly. Everything locks up.
So to fix the jammed door, you obviously don't add more people banging on it. You implement a circuit breaker.
Yes, the circuit breaker pattern is a lifesaver here.
It's just like the electrical breaker panel in your house. It has 3 states, right? Closed, open, and half open.
Right. In the closed state, traffic just flows normally,
Right.
but the breaker is constantly monitoring your failure or latency rate.
And the second that rate crosses your acceptable threshold, bam, the breaker trips to open. It instantly severs the connection, it fails fast, and it returns an immediate error to the user.
Which I know sounds super counterintuitive. I mean, why would you intentionally return an error?
Because dropping that traffic gives the struggling dependency time to clear its backlog. It lets it cool down.
Exactly. And then after a set period, the breaker transitions to that third state, the half-open state.
So it lets a tiny trickle of trial requests through to test the waters.
Right. If those trial requests succeed, it closes the circuit and restores full traffic. But if they fail, it trips right back to open.
You are basically sacrificing a small percentage of requests to prevent a cascading platform collapse.
It's a necessary trade-off.
Mm-hmm.
And speaking of trade-offs, once you've horizontally scaled and protected your fleet with circuit breakers, you immediately hit the very next physical constraint.
The speed of light versus the accuracy of your data.
Yes, the classic CAP theorem. It dictates that in the event of a network partition, a distributed data store can only guarantee consistency or availability, never both.
But the manual pushes this further into Pace-LC.
Yeah, PACE-LC. What's so fascinating here is that it forces architects to be honest about their trade-offs, even when the network is perfectly healthy.
Right, because it stands for if there is a partition, how do you trade off availability and consistency?
And the ELC part means else, meaning during normal operations, how do you trade off latency and consistency?
Yeah.
Because you just cannot have instantaneous responses and globally perfect data synchronization at the same time.
You just can't. So you use read replicas to handle massive read volume. But propagating writes to those replicas takes time, sometimes milliseconds or even seconds.
Exactly. You are offering the user an illusion of now.
Right. A classic fix for this is the read your own writes pattern.
Yeah. How does that work in practice?
Well, say you place an order on an e-commerce site. The system sets a flag on your specific session. So your very next page load is routed directly to the primary, strongly consistent database.
Oh, I see. So you see your order history immediately.
Exactly. While everyone else just browsing the site gets routed to the slightly stale but much faster read replicas.
That makes total sense. And we also aggressively use caching to drive that latency down. I mean, the math on cached economics is staggering.
Walk us through it.
Okay, imagine a standard database read takes about 40 milliseconds. But pulling that same data from an in-memory cache takes maybe 2 milliseconds.
Huge difference.
Right. If your system finds the data in the cache, which is your cache hit rate, let's say 70% of the time, your average latency is going to be roughly 13.4 milliseconds.
But if you refine your caching strategy and you push that hit rate up to 95%, your average latency plunges to roughly 3.9 milliseconds.
Yes. And you didn't rewrite a single line of your core application code. You just optimize how often you avoid hitting the actual disk.
Okay, but I have to push back here for a second.
Go for it.
We're talking about read replicas, caching, Pace-LC. Honestly, this all sounds like traditional 2015 web architecture. How does this actually apply to an AI chatbot? A large language model doesn't query a SQL database the same way a web app does.
That is the exact trap that so many builders fall into. They think AI is just totally different. But look at the AI twist here.
Oh, what's the twist?
An AI agent operates over multiple steps, right? It has to store its context, its its intermediate steps in a shared memory store.
Oh, right. Because if the compute node running the agent dies, another node has to be able to pick it up where it left off.
Exactly. That agent memory is a distributed systems problem. It faces the exact same CAP and Pace-LC constraints.
Right. Because when the agent is planning its next step, you have to ask, does it need the absolute, strongly consistent latest state of the world?
Yes. And if it does, it has to wait for disk writes, and your time to first token just spikes.
But if it can tolerate a slightly stale view from a cache, it moves way faster. but then it risks acting on outdated information.
Spot on. Which brings us to the really defining shift of the AI era. If AI inherits all those traditional constraints, what are the actual new rules it brings to the table?
Because the workload profile of a neural network is just fundamentally different from a standard web server.
Totally different.
Yeah.
The primary shift is moving from deterministic systems to probabilistic systems.
Meaning traditional software is a binary pass or fail. The exact same input yields the exact same output.
Right, but AI systems output a probability distribution. There's a range of correctness. And the economics change completely too. We aren't measuring cost purely in CPU cycles or memory gigabytes anymore.
Right. The new atomic unit of work and cost is the token.
Exactly, the token. And in a production environment, we are talking about inference, not training.
Which is a huge distinction. Training is this massive, months-long batch job. Inference is happening live, with a user sitting there staring at a loading spinner.
Right. And to make inference economically viable on these insanely expensive GPUs, you have to batch multiple user requests together.
So you're trading a small amount of latency to get massive hardware throughput.
Yes, and this is exactly where teams run face first into the 200 concurrent user trap.
Oh, the hardware sizing trap. Break this down because it's wild.
Well, everyone just assumes that if a model's weights fit into the GPU's memory, you're good to go.
Yeah.
But they completely forget about the key value cache, the KV cache.
What does that actually do?
It's the memory the model needs to hold the context of the ongoing conversation. That way it doesn't have to recompute the entire chat history every single time it generates a new word.
Ah, okay. So for an active, long context conversation, that KV cache might consume, what, 0.5 gigabytes of GPU memory per user?
Yeah, half a gigabyte is a solid estimate. So let's do the math on 200 users.
Okay, 200 times half a gigabyte is 100 gigabytes of memory strictly just for the conversation cache.
Exactly. And if you're running a standard 80 gigabyte GPU and the model weights themselves take up, say, 20 gigabytes?
That means you only have 60 gigabytes left for the cache.
Right. So you max out at roughly 120 users.
Wow. So to hit 200 concurrent users, you need 2 GPUs, not 1.
Yep. Skipping this specific math is exactly why a localized demo works flawlessly on a developer's laptop, but then completely crashes without a memory errors the second it hits production traffic.
Okay, here's where it gets really interesting for me. How we batch those user requests to optimize that memory has completely transformed.
Oh yeah, the industry moved fast on this.
Historically, we used static batching, and the way I picture it, it's like a roller coaster.
A roller coaster. Okay, I like that.
Yeah. A group of people gets on the ride starts, and even if someone finishes their specific sequence early, the hardware is totally locked up. Anyone new has to wait in line until the entire ride finishes and all the cars come back to the station.
Exactly. It wastes immense compute capacity because it has to pad shorter sequences to match the longest one in the batch.
Right. But the modern approach is continuous batching.
Which is such a game changer.
It is. Continuous batching is like a moving walkway at an airport. Tokens step on and step off dynamically.
Right. The moment one user's sequence finishes, a new user's prompt is injected right into the very next iteration. The system literally never stops moving.
It's brilliant. And to pull that off, engineers rely on something called page attention.
Yeah, page attention is fascinating. It's a memory management technique borrowed directly from how operating systems manage virtual memory.
So instead of forcing the KV cache for a user to occupy one giant contiguous block of memory,
Which leads to massive fragmentation and just wasted space.
right. Instead of that, paged attention breaks the cache into small, fixed-size blocks. And these blocks can be stored anywhere in the GPU memory and just mapped dynamically.
It's so efficient. And to squeeze out even more speed, you also have speculative decoding.
Oh, this is the giraffe model concept, right?
Exactly. So instead of having your massive, say, 70 billion parameter model slowly generate one single word at a time, you use a tiny lightning-fast draft model to guess the next 5 or 6 words.
And then you pass that entire guess sequence to the massive target model.
Right, because neural networks can process multiple tokens in parallel during a forward pass. So the large model can actually verify all 6 guessed words simultaneously.
That's incredible. If the draft model guessed correctly, you just generated 6 tokens in the time it usually takes to generate 1.
Yes, but all of this dictates a mandatory architectural rule, which is workload separation.
You cannot mix traffic types.
No, absolutely not. You have to keep your latency-sensitive, continuous batching chat users on one dedicated pool of GPUs that is tuned specifically for speed.
And you route your heavy offline document processing jobs to a totally separate pool tuned for maximum static throughput.
Exactly. You can't have a background job summarizing a massive PDF, stealing GPU cycles from a user waiting for a live text message.
Makes total sense. Sizing the GPU solves the speed problem, but, well, a fast model is completely useless if it just confidently hallucinates.
Yes, speed doesn't matter if the answer is wrong.
Right. So how do we give these models real-world data and the actual ability to act without hallucinating?
That is where you implement Retrieval Augmented Generation, or RAG. It's basically how we bypass the fixed knowledge cutoff of a pre-trained model,
Right. You take your proprietary company data and you process it through an embedding model.
which converts all that raw text into embeddings. These are basically dense vectors of numbers floating around in a high-dimensional space.
It turns fuzzy human meaning into computable math. So you store these vectors in a vector database.
Yep. And when a user asks a question, you embed their query, and you execute a nearest neighbor search.
So you aren't looking for exact keyword matches. You're actually looking for the mathematical proximity of concepts.
Exactly. But flat vector retrieval has some pretty severe limitations.
Oh, like what?
Well, it treats every chunk of text as an isolated island. So if a user asks a complex, multi-hop question,
Like, say, did the person who wrote the Q3 compliance report also approve the recent budget increase?
yes, perfect example. Flat retrieval usually fails on that, because the vector for compliance report and the vector for budget increase might be mathematically really far apart, even if the exact same employee is linked to both of them.
Ah, I see. Which is why architectures are shifting toward graph-based retrieval.
Exactly. Graph RAC. You pair the vector search with a knowledge graph.
So a graph database stores data as nodes and edges, creating these explicit semantic relationships. Like employee A wrote report B, and employee A approved budget C.
Right, so the retrieval system can actually traverse those explicit relationships. It totally solves those missing relationship bugs that plague standard RG implementations.
Okay, so you've grounded the model with accurate data. But how do you give it agency? How does it actually do things?
This is where we cross into agents. You give the model tools.
Tools, so it can query an external API or execute code or write to a database.
Yes. And the industry is rapidly adopting the Model Context Protocol, or MCP. It's becoming the open standard for integrating these tools inside secure sandboxed environments.
Okay, but wait, I have to ask, isn't an agent just a fancy bash script? I mean, we've had automation scripts hitting APIs for 30 years.
I hear that a lot, but the core distinction is non-determinism. And it completely changes your entire security posture.
How so?
Well, a traditional script executes exactly what a human engineer hard-coded
Right,
in the exact sequence they defined.
right. It's totally predictable.
But an agent receives a high-level goal. It evaluates the tools available to it via MCP, and it dynamically plans its own call graph. It might choose a sequence of actions that no engineer ever anticipated.
Wow. And that leads to probably the most terrifying post-mortem pattern in the manual, security failures with agents.
Oh yeah, they rarely happen because the model's actual weights were hacked.
They fail because of a lack of scope.
Exactly. Scope creep. Let's say an engineer gives an agent a database tool, and they carelessly grant it both read and write credentials, even though the specific task it was designed for only requires reading data.
Okay, so then a user submits an adversarial prompt, or maybe the agent pulls in a retrieved document that contains a hidden prompt injection attack.
Right. The model processes that malicious instruction, gets confused about its core directive, and suddenly realizes it has an active tool with write permissions.
And it decides to use that permission to just drop a critical table in your database.
It happens.
It's the new appliance literally burning the house down.
Exactly. And the only defense against that is the relentless application of zero-trust architecture and the principle of least privilege.
Meaning you just do not trust the agent.
Never. Every single tool must be scoped to the absolute narrowest permission mathematically possible, and you should use short-lived tokens. The agent is only ever as dangerous as the blast radius you explicitly provide it.
Okay, so let's zoom out. Let's say you do everything right.
Okay.
You've built a horizontally scaled N-1 resilient system. You have circuit breakers. Your KV cache is perfectly sized with page attention.
You've got your graph-based RAG and zero-trust tools.
Yes. You deploy to production. It's blazing fast. The users absolutely love it. And then 6 weeks go by and it just starts failing silently. The answers just degrade. Why does that happen?
Because of drift. We call this the silent break. In classical software engineering, if the code doesn't change, the behavior doesn't change. But an AI system's behavior is dictated by its input distribution. And over time, the real-world data your users are inputting slowly diverges from the static data set the model was originally evaluated on.
So what does this all actually mean for the engineer holding the pager at 2 a.m.?
It's a nightmare for them, because a standard observability dashboard tracking 500 server errors or latency spikes, it's going to show all green.
Right, because the server is technically up, the network is fast, the API is returning a 200 OK status.
Yeah, it's returning a 200 OK. It's just returning a completely hallucinated, terrible answer.
Wow, that is exactly the blind spot that gave rise to MLOps, right? Machine learning operations?
It is. It forces data science and production engineering to merge. Traditional observability relies on 3 pillars, which are logs, metrics, and traces.
But MLOps demands a 4th pillar, evaluation traces.
Exactly. You have to capture the exact prompt, the specific chunks retrieved from the graph database, the model's final answer, and all the metadata about why it chose that path.
But wait, if you're operating at scale, you can't realistically have a team of human engineers reading millions of chat logs every single day.
You can't. That's why you deploy an automated judge.
An automated judge, how does that work?
You use a second, totally distinct AI model. Usually it's a larger, slower, much more capable model, and it asynchronously scores the interactions of your primary production model.
Ah, I see. So it evaluates massive volumes of traces against a really strict rubric. It checks for things like faithfulness to the retrieved documents, relevance to the user's prompt, and general safety.
Right. It flags the suspicious interactions and leaves only those really tricky edge cases for actual human review.
And when you analyze those flagged cases, the root cause of the drift is usually just environmental.
Almost always. Maybe there was a seasonal shift in how users phrase their questions.
Or maybe a competitor launched a new feature and users are suddenly asking your agent to compare products it has literally never heard of.
Exactly. The automated judge catches that the relevance score is suddenly dropping.
Which means MLOps requires a massive cultural shift. An engineering team has to treat a sudden drop in an automated judge's quality score with the exact same severity as a massive spike in traditional server errors.
Yes, it has to trigger a real incident response. And the fix isn't just deploying a hotfix to the code base. It's procedural.
You have to continuously refresh your evaluation data sets with the new real-world data distributions so your automated tests actually reflect current reality.
You nailed it. And this all really drives home the core thesis of the manual. The AI layer doesn't just sit beside your traditional tech stack like some isolated magical black box.
No, it sits firmly inside it. It shares the same network edge, the same database connections, and the exact same identity and access management spine.
It inherits every single physical constraint of scale, state, and latency we've talked about, and then it layers the profound complexity of probabilistic outcomes right on top of them.
Which is exactly why Vidyut Haran leaves us with a critical 6-question checklist. It's basically a scorecard for any architect walking into a design review for a new AI feature.
Yeah, it's a great list.
Let's run through them quickly for the listener. 1, have you explicitly defined your 4 numbers for scale and latency? 2, where does your agent state live when a compute node inevitably dies?
3, what is your pace-LC trade-off for that specific memory? And 4, how does the system degrade during a dependency stall?
5, what is the continuous evaluation gate for your model? And finally, 6, what is the narrowest possible permission for your agent's tools?
Right, and a blank answer to any of those 6 questions is an unacceptable risk. It means you are making a massive architectural trade-off by accident rather than by design.
Absolutely. Well, for everyone listening, I want to leave you with a final thought to mull over, something that builds on that idea of the automated judge we just talked about.
Oh, this is a good one.
We just established that we are relying on a second AI model to monitor our production AI models for drift. But you have to ask, who is monitoring the judges? What happens when the automated judge itself begins to grift over time? What if it subtly shifts its internal rubric of what it considers a safe or accurate answer? It's basically a turtles all the way down problem that the industry is only just beginning to grapple with.
It is a really sobering thought, but it's exactly the kind of critical systems-level thinking this entire framework demands from you.
We highly encourage you to take these constraints and that checklist into your next engineering planning session.
Yeah, please do. Do not let the allure of a shiny new model distract you from the actual mechanics of the system holding it up.
Because at the end of the day, before you plug in that massive hyper-advanced AI appliance, you better make sure the house wiring can handle the load. Thank you so much for joining us, and we'll see you on the next deep dive.